Hello, good afternoon. My name is Beta with MIDAS. I welcome you for part two of our training webinar series called for performance-based seismic design as per CSA S690. As today is part two of our session, part one, we kind of covered details about the overall aspects to performance-based design, the basics of this. And then also the second learning objective was actually based on the recommendations related to performance-based design, starting with response spectrum. Today, the main objective will be on pushover analysis. So first, to understand the concepts of nonlinearity and the soil spring definitions. Second, to learn the techniques to compute the rebar and the concrete strains for the plastic hinge locations. And third, to conduct pushover analysis on a portal pier system and to evaluate the performances. Without further ado, I'm going to pass this along to our presenter and trainer for the day. His name is Prathamesh Vane. He is one of our leading technical specialists, also who has experience and masters in seismic design. I'll pass this over to Prathamesh now. And please, if there's any issues or any questions you have, please utilize the questions tab to indicate to us, and we'll respond accordingly. Thank you.
Thank you so much, Beda, for the introduction. So, without further ado, let us go to the presentation straight away. So, the contents of today's presentation will touch upon the nonlinearity concepts. Then we will look into the plastic hinge considerations and application in MIDAS Civil. Then we will continue with our previous problem with respect to the integral bridge. So we dealt with the response spectrum analysis to compute the demand. Now for the capacity, we will carry out a pushover analysis onto the structure to interpret its performance. So before going into the modeling aspects and seeing the results with respect to the model that we have created earlier, I would like to touch upon the concepts of nonlinearity and how do we consider it in MIDAS Civil. So as we know, there are in all three types of nonlinearity that we can categorize into: a material nonlinearity, section nonlinearity, and member level nonlinearity. So in case of a material nonlinearity, we will be considering the steel and the concrete. Then this discussion could be extended to the section as a whole, may it be a rectangular section or a circular section, depending upon your column sizes and shape. And the section nonlinearity then can be extended to the member level nonlinearity, that is your pier. So let us see how this affects in the analysis so far. So when it comes to the material nonlinearity, so herein in this particular structure, in this particular graph, we can see that it is a very common Manders model graph that we could see. The top curve is basically the stress strain curve for the confined concrete, as well as the bottom curve is a stress strain curve for the unconfined concrete. So from this particular figure, we can readily see that if the concrete is unconfined, then the strength which it is having is very, very less as compared to the one which is confined. So the confinement provided in terms of the hoop reinforcement or the stirrups plays a very important role in case of analyzing a structure for a performance-based design approach. So we know that larger the ductility for a system, more is the energy dissipation. And as we have discussed previously, that the energy dissipation or the seismic performance of the structure under any earthquake event largely depends upon the strength or the stiffness of the structure and the ductility of the structure. We also seen that it is not the strength which is having a higher say, but it is the ductility which is having the higher say. Can say that 80% of the structure energy dissipation depends upon the ductility rather than the strength. and only 20% criteria that we could say can be governed by the strength so far. So more the ductile structure, more the energy dissipation, and better is the performance. So there are different sections been shown in this particular figure. So we these are the general sections that we generally see in case of a pier, a circular section or a rectangular section. So the difference in this is with respect to the reinforcing stirrups which are being provided. So if you see that in the section, the both the rectangular sections which are shown here, the section size is same. It means that the stiffness is same, but the amount of longitudinal reinforcement is different, and also the confining stirrups. So if you see this particular graph that was plotted by Anders before, so you could see that all the sections A, B, C, and D are having a same size, but you could see that the performance of the structure section 4C 412, that is the section C, the strength is higher as well as the ductility as compared to the section 4A 48, which is my section A. So the size of the section A and section C is same, but because of the confining reinforcement which is given in this particular section, the average column strain which is generated and the strength which is generated for this particular section is very high. So we shall know the importance of the ductile detailing that we do in case of a column reinforcement. It is not only the confined concrete which is to be considered, but it is also the reinforcing steel that we are using. So this graph basically shows the different reinforcing steels or different types of steel which are used in bridge structure. So we could see that for the mild steel, the strength is less, but the ductility or the maximum strain or the ultimate strain is very high. But as the grade of the steel is increasing, the strength is increasing, but the ductility is reducing by far. So, as an engineer, it is a general tendency that if we are using the higher grade of steel, then in that case we are considering a higher strength and higher ductility in the structure, and my structure is more stronger. But this graph shows a very contradictory behavior to the general idealization that we are having. So, depending upon the grade of steel that we are using, so if you see that for the strings which are generally used in the cable state or the wires which are generally used in the cable state, the strength is very high, the ductility is very low, and hence they will be susceptible to breakage, and we need to check for that as well. So it is not that if we are using higher strength of steel, we are making stronger structures or stronger bridges. So many of the codes also give a certain limitation on the strength of the structural steel that is to be used in the bridge, so that the ductility of the structure is not compromised for. Now, with this background, let us talk about the section nonlinearity. So there are two types of section which are given here. One is the RC section and other is a steel type of section. So if we check this particular section, so this is the general stress strain curve that we generally see. So the strains uh, at the top is basically epsilon C, and at the bottom, that is at the reinforcement level, it is called as epsilon S. And the angle which is subtended by this strain line with respect to the vertical is called as phi or R curvature. The curvature is one of the most important entity that we need to deal with when we are considering nonlinearity in a structure. So the stress curve which is generated is very common, a parabolic for concrete, then a small amount of strain with respect to the FT, and Fs are basically stresses with respect to the tensile reinforcement. So the generation of this stress strain curves for concrete is taking place at each point. So what we do is we increase the strain at the concrete level up to its limit, and we compute what is the corresponding stress, and on that basis we plot a graph which is called as a moment curvature curve. So the amount of moment which is generated in that particular section at one particular curvature is plotted in a moment curvature format. So if you do this exercise for n number of points, then we'll get a curve something like this. So it is very well visible that this curve is non-linear in nature. So if you look at the section initially, so what we could see is there is a straight line, so which is nothing but my my stiffness, uncracked stiffness. Once there is cracking in the concrete that we see, then there is a certain reduction in the stiffness of the section, and there is a straight line up till the point where either there is um, yielding of the first rebar. So once the rebar has yielded, the section goes into a nonlinear zone, and we see um, we see that the section has yielded, and it goes up till and unless where we can see the rupture of the reinforcing steel, or there is a crushing of the core concrete. So this curve is been plotted. Now, most of the times what we require is the idealization of this particular curve. So to idealize this curve, there are different methodologies which are used. So one of the method to idealize is depending upon the equal area principle. So on that basis, the equal areas for the bilinear curve uh, is considered, and the point which is called as Mn, which is our notional point, is basically indicating the notional moment, and the curvature corresponding to that notional point is called as the yield curvature. So the ultimate curvature and the yield curvature, when we consider that ratio, it is called as the ductility or the curvature ductility. So in this way, a moment curvature curve for one particular section is developed. So once we develop a particular moment curvature curve for a section, now the discussion can be initiated with respect to the member level nonlinearity. So for the member level nonlinearity, so I'm considering a very simple structure, which is a single pier. So at the top of the pier, we are applying a force F at height h, and on that basis, the moment diagram is something like this, and the corresponding curvature diagram looks something like this. So if we are plotting a graph of applied force at the top versus the displacement, then in that case, the curve that we are getting is something like this. This is the force, this is called as a force displacement curve, or in other words, it is also called as a capacity curve. So in case of the capacity curve, similar kind of idealization with respect to bilinear capacity curve can be done to compute the ductility in terms of delta U upon delta Y, that is the ultimate displacement upon the yield displacement. So this ductility is called as the displacement ductility. So there are different types of ductilities. Once we saw in the previous slide, it was curvature ductility, and this is called as the displacement ductility. The formulas to compute the displacement ductility in this case are given in many literatures. So a common formula is being given here. So delta U is equal to delta Y plus phi U minus phi Y LP into H. So the value of LP that we see here is nothing but our uh, plastic hinge length. So the computation of the plastic hinge length is dependent upon the type of the section that we are using. So many authors have given different ways to compute the plastic hinge length. So in this particular curve, so if you recall our previous slide wherein we saw the curvature curve, so similar curve is being plotted here with respect to height of the column to the curvature, and we know that it is a non-linear type of a curve that we see. At the base, we will get the highest curvature, while at the top, the curvature is zero, where the displacement is the highest, the curvature is zero. So for this particular curve, we need to find the plastic hinge length, or for this particular element or the members, we need to find the plastic hinge length. Now, the computation of the plastic hinge length, which is LP, is based on the idealization of this particular nonlinear curve into an equivalent triangular and a parallelogram, which is seen here. Now, this is purely experimental basis as well as from the past experiences in the earthquake. So, researchers have calculated the plastic hinge length LP by um, checking the results or the data which is obtained from the past earthquakes, and by applying a quasi permanent type of a load at the top of the pier in an experimental laboratory, we compute the plastic hinge length LP. So the idealization in this case, which was found, was on the basis of a triangle and a parallelogram, and the area of this both the nonlinear curve and the idealized uh, uh, curve is basically the way in which LP is computed. So the point at which this linear to yield line intersects at the base is called as the phi y, so which is my yield curvature, and after that, so all after that, the rest of the place we called it as the plastic curvature, and the total phi y plus phi p is basically our ultimate curvature in that case. Now the length LP is, as I said, it is computed on the experimental basis. There is also a certain length which is called as the LSP. Now LSP in here is nothing but a length of strain penetration. So it can be very well known fact that, like, when we are having a structure which like a column which will be connected to a pier cap or a pile cap, so there will be a certain strain which will be penetrated inside the pile cap or the pier cap. So that particular length of strain penetration is called as LSP, and it is part of the plastic hinge length LP. Now the plastic hinge length calculations, depending upon the different types of codes that we are using, is different. So if you refer to Caltrans, the plastic hinge length computation depends upon the total length as well as the section type that we are considering. But in case of CSA 619, the computation of the plastic hinge length depends upon four factors altogether. So the section size, the total length of the column, uh, then there is a minimum section dimension for the calculation of LP, which is given, and this can be referred to CSA as 690. So we will look into how do we consider the plastic hinge length in case of different columns. Next concept that we need to know is with respect to the chord rotation. So in this particular figure, there are two types of structures which are generally seen. One is the cantilever kind of a structure where which can be easily seen in case of a simply supported bridges, and Then there is this structure in case of double curvature, where it can be seen in case of an integral bridge. So the quad rotation is not a new concept. It is similar to the one that we see in AISC as well for different beams and columns in a buildings. So this is nothing but the drift that we could say. So the quad rotation in this case, that is theta, is nothing but total displacement or the relative displacement of the column divided by the total height of the column. And this can be divided in this form. So if you are going to consider that there is a similarity on the basis of the deformations that we are getting at the center, then in that case the theta is nothing but delta by 2 divided by h by 2, which is nothing but delta by h again. So that is nothing but the chord rotation, or in other words, we also call desired drift. This drift is basically used to compute the demand and the capacity, as we saw in the previous seminar as well, wherein the drift of the bridge was computed under the response spectrum analysis. Now, continuing to my discussion on nonlinear modeling. So there are selection of the modeling approach depends upon the ability of model to simulate it accurately. So we need to consider the stiffness degradation, the strength degradation, as well as pinching if we are going to consider the nonlinear time history analysis. So this type of effects shall be accurately considered when we are going to model a nonlinear plastic hinge in case of pushover, as well as the nonlinear time history analysis. So to consider this, there are different modeling approaches proposed. So the to simulate this effect, there is a quantum model that we could do, or a distributed inelasticity model, or a lumped plasticity model. So let us see one by one what these are and how do we consider this in MIDAS 7. So the quantum model is basically a model with respect to the solid elements, all in all, and the computation of this kind of modeling are very difficult. The reason being the time required to analyze this structure is very large, and the amount of data or results which are produced in this kind of modeling is very large, and it is very difficult to extract the results from the quantum model. So engineers simplified this type of structure to use a distributed inelasticity model. So in case of a distributed inelasticity model, so we could see that the entire quantum model is now replaced by modeling the nonlinearity and different types of sections. So in this entire structure, the the entire beam or a column is divided into a certain section, and these sections are basically called as the integration points, and the nonlinearity in this case is computed at these integration point itself. So the computation of the moment and the curvature will take place at the integration points. So this is a more sort of a modification that we are making to the continuum model to reduce the amount of time and the reduce the amount of results which are generated. Then a far more simpler model with respect to the distributed elasticity model, it's called as a lumped plasticity model. So in case of the lumped plasticity model, what we do is rather than dividing the entire member into different kind of sections, we divide the member, or we consider only the points wherein the plastic hinge formation has a greatest possibility. So the plastic hinge region in this case will be in case of beam will be at the ends wherein the maximum bending moment can be simulated. So in this case, The plastic hinge region is this. So this is the length LP that we are considering, and there is only one single point at which the plastic hinge computation or the results computation will be going on. So the lumped plasticity model is the most simple model that we have, and it is considered as it is far more okay to use this particular model in case of in analysis to get uh, some results which are approximate but are considered to be accurate. So this type of modeling we can do in two options are available. One, we can do a fiber hinge model as in here, or we can go for a moment rotation hinge model. In case of MIDAS Civil Annex, we are having the three options to compute the properties for a moment rotation curve. So the first thing is the moment rotation m theta, then moment curvature m phi, and moment curvature distributed. So all the models that we discussed earlier are actually available in MIDAS Civil Annex for the computation. So if we choose the moment rotation type of a model, then we can model the moment curvature nonlinearity in case of a plastic hinge with the help of a bilinear type, a trilinear type, or a FEMA type of a curve. So it is based on the type of the interaction that we want to see in. So if you want to see uh, no interaction between the axial force and the bending moment generated in a column, then we can choose the interaction type to be none. In case of you want to see the interaction between the axial force and the bending moment which is generated and the variation of the moment curvature curve with respect to the axial force, then we can set it to PM or PMM status determination. If we are choosing a distributed type of a model in case of in case to create a plastic hinge, then in that case the integration points are distributed in a particular section in case of a Gauss-Labato integration. So you could see that the integration points are not actually distributed equally, but these are distributed on the basis of the Gaussian approach. So we need to take care about how and at which point the integration is happening. Similarly, if we set the integration points in lumped type, then in that case, the integration point or the data could be computed at the center or it could be computed at the end. So, so for the entire element, if LP1 is my plastic hinge, then in that case, if we choose the center, then at the between the whole length of the plastic hinge, the center will be used to compute the moment curvature data. While if we choose the end, then the extreme ends of that particular element will be used to compute the data. So similarly, if we are using a moment curvature type of curve, but with the PMM interaction, then the program will compute different moment curvature curves depending upon the different axial loads coming on to that point. So all this type of options are possible. So let us see one of the example that we have created for the same. So this is one of the structure. It's a very simple structure that we could see. It is a portal frame over which the sulfate and the axial load of 450 kilonewton is applied. And the probable plastic hinge locations in this case are nothing but my top of the column and the bottom of the column in that case. Now we have assigned the plastic hinges in this particular system. So if I had to show you the properties that we are considering here, it is a moment curvature type of a plastic hinge, and the plastic hinge length which has been considered here in this case is 0.49 of the element length. So it means that the division of the element, the half of the element is considered to be plastic, is having a plastic hinge. The type of the skeleton curve is bilinear type that I'm considering here. So if you see that this is basically nothing but my moment curvature data for this particular section. Now I have set the moment curvature data to auto calculate, so the program can automatically calculate the moment curvature relationships in this case and use it depending upon our calculations. So as this is not interaction type is set to be none, it means that only one single axial force will be used in calculation of the moment curvature curve. Now the question is which axial force should be used. Now, I'm considering a non-interaction in this case. The reason being this structure is very, very simple and there is no variation of axial force when we will be carrying out the push-over analysis on this particular structure. But if you are modeling a structure which is having, which is a global structure and which is having multiple bends, then in that case, there could be redistribution of load when a plastic hinge is formed at one particular location. So it is very important that if we are using a global model in the analysis with multiple bends and multiple probable plastic hinge locations, then in that case, we shall consider the PMM interaction in that case to determine the accurate computation of the plastic hinge mechanism in that particular structure. So in this way, we can actually utilize the moment curvature curve and the bilinear type of the skeleton curve in the analysis. Now, the other question is like the hinge length, which is set up here is 0.49, and that the reason for that is, so if I turn on the extruded view, you'll see that I have divided the entire element into some parts, right? So this is not a single column section, but it is divided into different elements. And the 0.49 is basically the ratio of the total length of the element upon the plastic hinge length. So what I'm telling to the program is like for the total length of this particular element, the lower half of this particular element will be my plastic hinge region. Similarly, on the other hand, the upper half of this particular element will be my plastic hinge region. So we need to check very carefully that if we are dividing the column, then in that case the plastic hinge ratio, that is LP upon L, is given correctly or not. So we are not going into the details of this particular structure because I have already shared one of the file wherein a detailed modeling of this particular structure and assigning of the plastic hinges in such kind of a structure is given. So you can follow through that to see the steps involved in the structure. So I'll just jump on to the results that I'm getting for the pushover analysis in this case. So the push load that I'm applying in this case is in the transverse direction that I'm having, that is this. So I'll just show you what are the deformations I'm getting in that case. So if I go to pushover and um, deformations and the deform shape, so I'll just click on apply. So you'll see that the push load is applied in the X direction, which is nothing but my transverse direction in this case. So the for one of the hinge that I'm having, I have generated the results for this. So for the push load that I have applied to one of the hinge, the moment curvature curve or the moment versus curvature data that I am getting from the pushover analysis is something like this. So as it is a bilinear type of a curve, you will see that even the results which are generated for this particular structure is bilinear, and after one point there is a certain yield in the structure that we are getting. So you can see that the yield is happening at a moment of around 1000 and the curvature upon about 0.6 into 10 power minus 3 per meter. So we can check the results in this case for this structure. So let me just hop on to the actual model that we have created. Um, but before that, uh, let's look at what are the different methodologies to evaluate the performance points. So in order to evaluate the performance of the structure, there are different methods which are used. So the capacity spectrum method or equivalent linearization method, wherein the uh, structure or the pushover curve or the capacity curve is been taken in such a way that an equivalent bilinear curve is obtained, and the capacity and the demand in that case are met at one particular point, and that point is basically called as our performance point. Other method is called as the displacement coefficient method, which is one of the more simpler method that we could say, depending upon the displacement that we will be getting on this particular structure. And this methodology is also given in performance-based design ASHTO 2023. So you can refer that particular code to see the outputs from the displacement coefficient methods. Similarly, there are certain tools that we could use. I cannot call them as methods, but the tools to compute the performance of the structure. So in case of the pushover analysis, the pushover analysis could be an adaptive pushover analysis or a multimodal pushover analysis. So the adaptive pushover analysis is one of the method in which the pushover analysis is carried out on a structure such that the uh, loading pattern in the pushover analysis is modified in each step depending upon the type of the deformation which is taking place and the plastic hinge formation in the structure at each location. There is a modification in the loading pattern and the the reason and that is the reason why it is called as an adaptive pushover analysis. Similarly, there is multimodal pushover analysis where multiple modes or the multiple eigenvectors of one particular structure are considered, and a linear combination of this particular modes has been done, and the loading pattern is applied on the basis of the linear combination that we are getting. However, we know that the eigenvalue analysis in itself is a linear method and is an superposition in this case, or the direct superposition in this case is not valid, and that is the reason why this method has not gained much popularity. So the type of pushover analysis that we will be carrying out in our structure will be with respect to the uniform acceleration method, or if the structure is symmetrical, then in that case we can also go for the loading pattern in case of the fundamental mode of that particular structure. So let us go to our bridge model that we were discussing earlier. So the details are something like this. So this is the same model that we are going to consider for the capacity computation, but just a recap. The location is basically British Columbia. Soil type is considered to be soft. Importance category, it is a lifeline structure, and the performance is to be evaluated as SP3. Response modification factor which is used in case of the response spectrum analysis was 5, and the performance level that which is expected from this particular structure is service limited. So for this particular structure, the results that we got for the response spectrum analysis in this case are something like this. So we got a demand drift in this case as 0.074 meter. So this is actually the deformations or the relative displacement that we got in case of the columns. And if you have to get the drift, actually we need to divide it by the height of the total column. But this is basically the relative deformation that we got. So this is nothing but the demand that we have got from the response spectrum analysis. Now it is time for us to compute the capacity and check the um, capacity of the demand and the capacity ratio for this particular structure. So for an engineer, it is very important to first specify what is the location of the plastic hinges or the probable plastic hinge location in the structure to actually assign the plastic hinges at that particular point, right? So it is very important for us to know at what all location the plastic hinges could form. So for this particular structure, I have considered the plastic hinge locations as shown. So in case of the columns, you can see that the plastic hinges are forming at the top and the bottom of the column. Then in case of the monopile, we could see that the plastic hinge could form at the location at the fixity or the point of the fixity in the monopile. Similarly, in case of the pile group, the plastic hinges could form at the point of fixity or at the base of the pile cap. So these are the basic plastic hinge location that we are dealing with. Now, the problem that we generally face here is how to um, find what is the point of fixity for this particular structure. So most of the engineers, what we do is we assign the plastic hinge throughout the length of the piles, so that depending upon the highest moment that we are getting at one particular point, the plastic hinge could form at that particular point. So one method is to assign the plastic hinge throughout. The second method is depending upon the approximate formulas that we are having to identify the point of fixity in the pile, we can specify the plastic hinge at that location. Now, the other concern that we need to address is the expectations from the model that we are doing. So it is very important that the plastic hinge in the structure shall form at the point where we are anticipating it to be. So we do not want a plastic hinge to be formed within the piles. The reason being the inspection and the repair of the plastic hinges, if formed within the pile, is very, very difficult. And to carry out that process, it becomes very, very difficult. So the engineers, as an engineer, what we want is the plastic hinge to be formed at the location wherein the inspection and the repair work can be done very easily. So in that case, the plastic hinge location is nothing but the anticipated plastic hinge location is nothing but within the columns, wherein we can do the repairs easily. So as a result, I want my structure such that my columns will form the plastic hinge first before the plastic hinge is formed within the piles. So what we'll do is we'll make our piles or the pile group such that they are more stronger than my column, so that the energy dissipation or the damage will happen in the columns first and not within the piles. The second important consideration that we need to note that uh, the plastic hinge or the energy dissipation does not happen within the superstructure. So the reason for that is we want our structure to be serviceable after the earthquake as well, and um, there shall be the traffic movement. There shall be no traffic movement disruption that we want. So that is the reason why we consider that our superstructure is will remain elastic, and we design our superstructure in such a way that it remains elastic throughout the seismic event. Now, we know that in case of buildings, the concept that we follow is a strong column, weak beam. But in case of the bridges, the concept is contradictory and completely reverse. Here, what we want is our beams to be stronger and columns to be weak. So it is completely reverse in case of bridges, and as an designer, we shall keep that thing in mind when we want to design the structure um, for a seismic event. So now with this background, I'll jump on to the model that we are having. So, so this is the model that we are having. Um, So we already saw the results for the response spectrum analysis in this case. So now let us completely go towards the pushover analysis. So in case of the pushover analysis, the creation of the pushover analysis setup is important. So firstly is the location of the plastic hinges, and secondly the characteristics or the definitions of the pushover hinges that we are assigning. So in this case, the pushover hinges that I'm considering here is within the piles. So if I had to display the pushover hinges, so these are the locations at which I have applied the pushover hinge. So you can see that the hinges are applied throughout the location of the pile. And in case of the column, as I have not divided the column, the plastic hinge looks as if it is in the center, but it is actually applied at the extreme ends of the column. So I'll just show what are the properties that I'm considering in this case. So it is actually a moment curvature or a lumped type of plastic hinge that I'm considering. So which is the most basic non-linearity that we consider. So the hinge length, if we check, is considered to be as 0.8185. So the LP upon L is 0.185 at both the ends. So this is computed on base of the plastic hinge length computation as per CSS 690. The interaction that I'm considering here is PM status determination. So as I'm only considering a pushover case in this bridge in case of the longitudinal direction. So now if you see that the properties of this pushover hinge are basically the GSD imported type. So as this is GSD imported, so the program automatically considered this as PMM type of interaction or PM type of interaction depending upon the case. So in MIDAS Civil NX, we are having this feature of General Section Designer, which is used to compute the moment curvature curves very easily. So I have already um, defined one of our column sections that we are using. So this particular section is basically imported from the file or the model that we are having, and I have defined the Mander's unconfined properties as you could see. So I have defined the Mander's property for this particular section, and then I have also defined the nonlinear properties for my rebar in case of the Park strain hardening model, which is as shown here. All the expected strength for the steel as well as the concrete were used for defining the moment curvature curve in this case. So if I click on the design in this case for this particular section, the moment curvature curve will be generated in here. Now this moment curvature curve, we can check the results for at different axial loads. So let us say that my axial load is around 5000 kilonewton at one point, and I just click on the display idealized. The program will generate an idealized moment curvature curve in this case. You can also see the stress strain curve in this case, and we can compute what is the concrete strain at the top and rebar strain at the bottom. You can export this particular data in MIDAS Civil Annex directly, and we can get the plastic hinge data for this particular section. So in this way, what I've done is I have used the GSD import type of the plastic hinge to assign it to my columns. So going back to the plastic hinges for the columns, so if I click on the yield surface properties and I'll just click on y-axis, so you could see that for the different axial forces, the moment curvature plot is being considered. So if I change the axial force, the moment curvature plot changes, and on that basis, the computation of the deformation in the sections are computed by the program. So if we are going to use the GSD imported type of hinge, the program automatically defines the different axial forces, and during the pushover analysis, as the axial force in the member changes, the moment curvature curve corresponding to that particular axial force is interpolated by the program and used in the analysis. So this gives us more accurate and reliable results. So once you define the types of the hinges and assign the different hinges, we can set up the pushover load case. So I have set up a pushover load case in the X direction. So the maximum translation that I'm considering is 0.7 meters. This is experience based. So depending upon the structure that you are modeling, you can push the structure to one particular limit, which is higher than the performance objective from that particular structure. The type of the loading pattern that we have considered in this case is uniform acceleration in the dx direction. So there are other loading pattern which are available as well, so that you can load the structure with respect to the mode shape, or you can also use the static load case in case of single column, that is a point load at the top, to load this particular structure in the incremental manner. So I have used the uniform acceleration case and load this particular structure until and unless a maximum of 0.7 meter deformation is visible on the global scale in this particular model. So this is basically my pushover load case that I'm considering for this structure. Now, this particular structure is already analyzed and the results are already computed in this case. So this is one of the pushover or the moment curvature curve that I'm getting for one of the hinge. So you could see that it is bilinear at a point, and once there is a rupture been formed, the strength of the column is completely reduced to zero. So this is the type of the GSD imported moment curvature data that we given and which can be seen. Now, once we are familiar with how we um, uh, generate the model, now let us see how we can verify the results in this case. So I'll just undisplay the hinges. So now let us go to the pushover, deformation, and the deformed shape. So I'll just click on apply. So this is my first step basically. So you'll see that the structure is basically deformed in the longitudinal x direction. Now I need to find the point wherein the first yield within the structure is happening, or what is the plastic hinge location in that case. So to do that, what I'm going to do is going to the results table and clicking on the yield step. So I'll just select my case and click on OK. I'll sort the dialog with respect to the rotation RY. So if I scroll down, we see that the first yield step, that is my first yield in this particular structure, is happening at the element number 2021 and at the step 110. So what I'm going to do is I'm going to the step 110. I'll turn on the performance or the element yield status and click on apply. Just turn on the legends as well. Just turn off the values. So this is basically my step number 110. The element number 221 or 2021 is basically my column. Okay. So we can very well see that as per our requirement that my first yield or the plastic hinge should form in the column and not in the pile is satisfied. Uh, so this is basically my first yield point that I'm getting. Now what I'm going to do is I have to specify the deformation in this case such that the strain limit has been achieved. So for this, let me switch back to the PPT. So in this case, I have to compute the strain. Now I'll find out the point at which I'm getting a strain of 0.25, which is my limiting strain for the service limited performance case. So if you remember and recall the CSS 619, then in that case, the limiting strain that the code asks us to consider is 0.025 in case of the steel rebars. So from the moment curvature curve, I need to find a point at which this strain is just limited. So from this uh, snip, we can see that the strain in the bottom rebar is just limited to 0.025. So the step at which this is happening is the step number 43. And if you check the results, the moment that we are getting in this case is 5432 kilonewton meter. So this step is basically at this particular point, and the curvature at that point is 0.02406. So we need to find the point at which we are getting this curvature in the program. So how to find the curvature related data is something like this. So I'll go to Civil Annex again. We can go to beam summary. We can select all the steps in the pusher analysis. We can select the push case, and I'm only going to see this results for the 2021 element, right? Just click on OK, click on RY, and as I discussed, we need to find the curvature which is 0.02406. So let us do that. So I'll just scroll down in this case. So these are basically my deformations, which are in the form of Ry, which is nothing but my curvature. So if we go to step number 358 in this case, so we can have the curvature related data, which is around 0.0246, we could say, and this is happening at the step number 358. So at the step number 358, the strain in the rebar is just limited to 0.025, which is recommended by CSA. And let us now check the deformation which are happening in the column at the step number 358. So I'll just go to step number 358, turn on the values and click on apply. So this is basically the drift that I'm getting. So the total deformation in this case in the column is 0.499 minus 0.241. So to compute the same, it is nothing but the capacity drift of around 0.257 meter. So for the service limited, epsilon s shall be limited to 0.025. The step at which this limit is achieved is the step number 358. The drift at that particular limit is 0.257 meter in the column, and the capacity drift is nothing but 0.257. So if we compare the demand drift that we got from the response spectrum analysis and the capacity drift from the pushover analysis, the demand to capacity ratio in this case is 32%, which is less than 100% or which is less than 1. Uh, this means that the service limited performance criteria for this structure is satisfied, and the range or the safety that we are getting is far more, that is around 68%. So this structure is actually very strong. To satisfy this particular performance limit, we can reduce the amount of reinforcement, or the section sizes can be reduced to increase this ratio to certain optimal level of around 80% or zero point 0.8. So similar results were computed for the maximum bearing displacement and the expansion joint, so which can be checked. So in this way, we can compute the strain levels in the structure for the performance based design. Now, once we achieve the performance could be underperforming or overperforming. As our structure was overperforming, there are certain uh, methodologies by which the optimal performance could be achieved. It could be achieved with respect to the strengthening, stiffening, or ductility enhancement. So in this case, if we are considering the strengthening, and so if you see, this is basically my demand curve and this is my capacity curve. So before strengthening, the structure was somewhere here. Once we strengthen the structure with respect to increasing the section size and the amount of reinforcement, the strength of the structure will increase, and so will be the performance. So the spectral displacement, or the performance point that we are getting at the intersection of the capacity and the demand spectrum, is this. But now, as we have strengthened the structure, the performance point that we are getting is somewhere here. So if your structure is underperforming, then in that case, we can do strengthening to increase its performance or reduce the spectral displacement in that case. The other method is stiffening. So by stiffening the structure, by providing the lateral bracings or other stiffening members in the structure, we can increase the stiffness. So you could see that firstly the stiffness of the structure was somewhere here, and once we increase the stiffness, the uh, the performance point is shifted uh, upward. And finally, there is ductility enhancement. If your structure is failing because of the shear failure of the entire structure, then we shall increase the ductility of the structure by providing additional ductile reinforcement or adhering to the ductility requirements for that particular section. And you could see that before the ductility enhancement, the structure was not even yielding. So the yield strength of this particular structure was very, very less, and it was failing very before the demand was reached. But once we give the proper uh, stirrups, or the ductile detailing is done accurately, you can see that the structure becomes more ductile as it is increasing its displacement capacity, and the performance point could be reached. So these are the three different methods that by which we can alter the performance of that particular structure. So finally, we saw what are the nonlinearity considerations, how to carry out the performance-based design in MIDAS Civil NX, and what are the different tools such as the general section designer in MIDAS Civil, which could be used for the performance-based design in bridges. So in the next uh, webinar, we will cover the CSX6 recommendation for the nonlinear time history analysis. We will select, we'll check how to select the compatible time history records. We'll see how the fiber models can be defined in MIDAS Civil and how the behavior can be checked. And finally, we will configure a numerical model for time history analysis of an entire structure. So uh, that was it from my end.
Okay, Prathamesh, thank you. Before he starts addressing some of the questions, we'd like to take this time for the attendees. If you guys have any questions, to please submit them in on the control panel. I want to address some few questions that people have. We've got quite a few from people asking very similar questions related to um, the first session. If there was any, like, there were some materials that they weren't able to download, or the recording for the session for session 1 and session 2. These sessions will be provided as a video recording. And also, initially, I was commenting about the materials and the other downloads. I was going to send it via email. However, if you look at the materials tab or the handout tab right now, I did include some of the handouts from the first session, part 1. So if you go to that session, that portion right now, you should see 2 additional files, an Excel sheet, along with another PDF that says 2-span PSE composite CSAS6. Both are available for you today. We did get more than 5 questions related to this, so I just wanted to address it before we go on to the actual technical questions. Okay, and the sessions will be provided. The recording for the session will be provided after today's session is over as well. Other than that, we'll get started with the queries that came in. And for everyone else, please submit your questions while we have this opportunity. Prathamesh, if you will.
So the first question, what setting optimizes the balance between accuracy and computational efficiency? So this is actually a very general question that has been uh, raised up here. So I'll consider that the accuracy and the efficiency is with respect to the plastic hinge definitions that we discussed earlier in the presentation. So as I said, uh, we have to maintain a balance between the time which is required for the computation of the global models and the amount of accuracy that we are getting. So if you are going with the quantum modeling, then in that case we are having a more accurate results, but the computational time is very high. But if we are using a lumped plasticity model, then in that case the accuracy is reduced, but the time duration for the computation is very small. So we need to provide a balance between that, and um, the practicing engineers or the researchers are using the lumped plasticity type of model, and they have seen that it is a very well or a good representation of the actual scenario. So even if it is very approximate, but it has historically given a better results. So we can go with the lumped plasticity model, even if it is not more accurate, but it is efficient to use. So addressing the second question, how do you calibrate the hinge for different components of the bridge? So the calibration of the hinge data is completely based on the type of the hinge that you are defining. So if you are using the concrete section, then we shall choose a plastic hinge model in such a way that the degradation in the concrete, the that is the stiffness degradation, as well as the pinching effects in the concrete are accurately considered uh, in the plastic hinge data. So the choice of the plastic hinge model is very large. So even in Midas, if we see, there are different types of plastic hinges which are available. It could be Takeda, it could be multilinear, bilinear, or trilinear, or FEMA type of plastic hinge. But all the plastic hinges uh, uh, depend upon the choice of the plastic hinge, depend upon the engineer directly. So we have seen that mostly engineers for the particular representation of the data in this pushover analysis, they will go for the bilinear type of a plastic hinge, or max to max they'll go for the trilinear type of the plastic hinge, which is a good representation of the hinge data. And regarding the calibration, so the calibration can be done on the basis of the moment curvature curve that is being generated for that particular section. So uh, uh, the best or the ideal plastic hinge uh, data for one particular section, if it's a different section, like it's a not a normal section, then in that case uh, uh, proper calibration is required from the moment curvature curve to capture those results. But for regular sections, a bilinear type of plastic hinge is okay to be used. Coming to the third question, how do you set up and evaluate the multi-directional loads? So for this, we know that when we are going to evaluate the response spectrum analysis, or even in the pushover analysis, in that case, what we want is the 100% in one direction and 30% in the other direction, that is the multi-directional loads are to be applied. So to cater for this, when we are considering the pushover load case, in that case, so what we have to do is uh, so let me just share my screen again for a moment. So what we have to do is, like, as I have in this particular example, I have only considered dx in one direction, and the scale factor is considered to be 1. So what will I do is I'll consider dy with a scale factor of, let's say, 0.3, that is 30%. Can add. So now you're having the multi-directional loads, that is the dx and the dy, under 30 rule. And similarly, the for dominant translation or the transverse direction, we can go as 100% of y and 30% of x for the push y case. So in this way, we can consider the multi-directional loads. Veda, if you could share the screen again. So coming to the fourth question, can concrete cracking and steel yielding be considered with MIDAS for seismic design? So the concrete cracking and steel yielding can be considered, um, but you know that for concrete cracking and yielding, it cannot be represented by a hinge or the plastic hinges that we have considered right now. For considering these, we need to define a fiber model, and for the simulation of the fiber model, we can do it in the nonlinear time history analysis. So the third session that we are having will be considering the fiber model, which will consider the cracking and the steel yielding in the seismic analysis. So for the fifth question, what are the applications for GSD? Do I need to this for a moment curvature? It is possible to set the graph. Is it possible to set the graph without it? So the application of GSD is mainly used to compute the moment curvature curve. And secondly, if you're having any arbitrary type of section, then you can design that particular section by using the GSD. So to generate the moment curvature curve, there are other methods also. So if you are using MIDAS Civil Annex currently, then in that case, if you go to the Properties tab and go to the the inelastic properties, you will see a moment curvature option. This moment curvature option can also be used to generate the moment curvature curve. If you are not using the GSD, the added advantage by using GSD is we can import the hinge properties directly from the GSD, but which cannot be done from the moment curvature data which is generated within Civil itself. So uh, that is the one thing. So coming to the sixth question, how can the computational time be optimized for the large pushover analysis without compromising the accuracy? So it 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 depends upon the way in which the structure is modeled. So if you see that in the model that we just saw, uh, I have assigned pushover hinges throughout the length of the pile, right? So assigning these many hinges is actually increasing the computational time of this particular structure very much. So if as a practicing engineer, we know that the location at which the location below the length of the fixity of the pile, we know that the plastic hinge won't be forming at that location. So there is no point of assigning the plastic hinge there. So this shall reduce the computational time. So knowing what is expected from the model and the locations at which the nonlinearity is modeled is very important. And if we optimally model the nonlinearity in that particular structure, the time required for the analysis can be reduced considerably in that case. So that is one of the method. So other methods could be using the none type of interaction or no interaction between um, uh, the axial force and the moment. So if you are quite confident about there is a very slight change in the axial force that we see in the structure during the pushover analysis, then we can set the structure data to no interaction with the axial force, and in that case the computational time can be reduced. But again, we will compromise on certain accuracy, so a balance is to be maintained in that case. So coming to the seventh question, how are the convergence addressed in MIDAS, especially for nonlinear behaviors? So the convergence in MIDAS are addressed by the tolerance which is set. So there are three types of tolerance limits that we can set. So one is with respect to the force, other is with respect to the deformation, and third is with respect to the energy. So the tolerance limits are set, and depending upon that, the convergence is addressed. So it is also an option is also provided in MIDAS to consider any one or all the tolerances limit. So generally, deformation tolerance is being considered in such type of analysis. So coming to the eighth question, can you comment on why do you come up with the reduced spectral curve as compared to using the elastic demand curve from RSA for demand side? Did you consider the R factor in the reduced spectral curve? Okay. So addressing the first sub question, so the reason that we have to reduce the spectral curve as compared to the elastic demand curve is we know that like when we compute the capacity of the structure, where the demand and the capacity curve are meeting, that is called as a performance point. So the point at which this is the intersection of the demand and the capacity curve is happening, at that particular point, we need to be sure that the damping in that particular structure is constant. So the demand and the capacity of that particular structure at performance point is having a same damping level. So to ensure that some same damping, um, we know that as the seismic event will be happening, the structure will be damaged and the damping will be increased. So we reduce the demand on the structure by increasing the damping. So we know that higher the damping, lower or lower is the demand on the structure, because as we increase the damping ratio, the demand curve reduces, or the spectral acceleration reduces. So to match that spectral acceleration in both the demand and the capacity, and to have the similar uh, 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 damping, we need to reduce the demand. So this can be also verified from the any performance based design theory book. We can see that there. And to address the second part of the question, did you consider the R factor in the reduced spectral curve? So the answer to this is yes. So for um, as I'm considering the uh, demand, I'm reducing it by the R factor to compute the spectral curves.
Okay, I think we're past the time right now. I would like to thank everyone for staying on and thank Prathamesh for taking the time to answer these questions in detail. Um, Again, the tutorials and some of the material, there are additional questions. Like I mentioned in the beginning, we will address those in a follow-up email. For the tutorial portion of it, the materials, like I mentioned, it is available to download in the materials tab. However, I will send this out again as an attachment for session one and session two. And session one and session two, well, session two, after the recording is completed, it will be posted up along with session one. And for those who are asking about the credit hours, again, the credit hours will be provided after the part three, the last part of the session next week. That way, we just have to send it out once. So regardless of whether or not you attended all three, our system will notate it, and we'll just provide the allocated credits based on the sessions you participated in. And last is our last part of this series, part three, for regarding time history, will be next week, same time at 3 p.m. Eastern time. You do not need to register if you have already registered. Um, uh, the GoToWebinar link will automatically send you another reminder and get back to you with this. So, everyone, I would like to thank you so much for your time today. Thank you for participating and joining in the session. Please, if you have any questions, feel free to reach out to us with more anything that you guys. Other than that, these are some of our contact information and some of our social media blogs. So please, we appreciate your time. We will see you next week. Thank you very much.